This video begins the next step in understanding attractions between molecules. I need to lay the background for you so that you can draw pictures of molecules and then understand which way the electrons shift that are actually in the bonds. So this is the first step in understanding that particular concept. So we're going to look at two things in this video. The first thing we're going to look at is valence electrons, and this is something that we did in the fall, so this is review. And the next thing is electronegativity difference. And how that affects polarity, what we call polarity, and we'll get to that in a minute. So we're going to start with valence electrons. You'll remember that if I was going to write, say, the electron configuration for an element like aluminum. So if I wrote the configuration for aluminum, we'd say it's got 13 electrons. You can see the 13 up here in the upper left-hand corner of the periodic table. So it would be 1s2. Second energy level has an S and a P, 2s and 2p. The P holds 6, and then the 3s would hold 2 electrons. And so far I'm up to 2, 4, 10, 12, and the 3p would have 1 in it. So that would make our 13 electrons for aluminum. It has 13 electrons and 13 protons, 13 electrons shown where they are within their sublevels. The ones we're concerned about in this unit are only the higher energy level electrons, the ones that are in the highest energy level. So if you look here, there are 3 of them. Now I want to call your attention to the periodic table. So this Roman numeral 1, Roman numeral 2, and then 3, Roman numeral 3, Roman numeral 4, Roman numeral 5, 6, 7, and 8. Notice that aluminum is in the Roman numeral 3 column, the third tall column, and so you'll notice that it has 3 electrons in its outer shell. So the number of valence electrons for aluminum would equal 3. All right, let's pick another element. What if we're doing phosphorus? So you'd find P on the periodic table. You go up and look and see what column it's in. It's got a Roman numeral 5. So phosphorus would have 5 valence electrons. So a couple more. If you did iodine, iodine's over here. It's in Roman numeral 7, so it's going to have 7 valence electrons. Now, just in case you don't believe me, here's the electron configuration for iodine. Iodine has 53 electrons and 53 protons, so 53. So you'd have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10. Now we're up to 5p. I think we're about there. 2 plus 2 is 4, plus 6 is 10, 12, 18, 2 is 20, 30, 36, 38, 48. Iodine is going to 53. So but all the way up to 53 will require 5 more of these. Okay, now if you look at the highest energy level, it's here in the 5s and here in the 5p. So these are the 2 highest energy levels. And what's the number of electrons? 2 here, 5 here. What's 2 plus 5? 7. All right, so just in case you didn't believe me, there it is. But all you have to do to find valence electrons is look at the column that the element's in. All right, so that was review part 1 of valence electrons. Review part 2, in this unit we're going to be adding valence electrons. So if we have, say, carbon dioxide, there's a chemical compound, you look at, to find the valence electrons in carbon dioxide, you'd look up here and say, well, carbon's in the 4th column, oxygen's in the 6th column. So carbon has 4, oxygen has 6, but there are 2 atoms of oxygen, so the total number of electrons for oxygen would be 12. There's only 1 atom of carbon, 4, so the total number of valence electrons in carbon dioxide would be 16. Okay, once again, valence, outer shell electron. If we were doing water, water has hydrogen and oxygen. So you'd say hydrogen, it's got 1, oxygen has 6. This is 1, that's 6, but there's 2 hydrogens, so that would be 2 plus 6 equals 8 valence electrons. That was plus. So 8 valence electrons in water. Valence means outer shell. All right, what if you're doing something something bigger, like say C6, H12, O6, and we want to know just the valence electrons. So we know carbon has 4, so it'd be 4, and hydrogen has 1, and oxygen has 6. So we'd have 4 times, there's 6 atoms of carbon, each one has 4, so it'd be 24. There's 12 atoms of hydrogen, each one has 1, so that's 12. And there's 6 atoms of oxygen, and each one has 6, so that's 36. So 24 and 12 is 36, plus 36 more, 72 valence electrons. So it's kind of like adding up molar weight, except that we're not using masses, we're using numbers of valence electrons. You find the valence electrons by just looking at the column that they're in. So here's one more example. Suppose you had CCl4. So you would look at carbon. Carbon has 4 valence electrons, see the Roman numeral. Chlorine is in this column over here with 7 valence electrons. But there are 4 atoms of chlorine, so that's going to be 4, because there's only 1 atom of carbon, plus 7 times 4. 4 plus 28. So you'd have 32 valence electrons in CCl4. 32. So that was a review of valence electrons. That's part 1 of this video. Part 2 of the video deals with electronegativity difference and polarity. And what we're going to be worrying about is if you have 2 atoms, which one is 2 atoms together, which end of the bond do the electrons move toward? So for example, if I have a bond between H and Cl, okay, so we want to know this line right here represents a pair of electrons. So there's 2 electrons in that bond. A pair of shared electrons. Okay, I want to know which atom would attract this pair of electrons more. So let's take a look at electronegativities. And I have a chart here. Okay, I will reference this on the website so you'll be able to find it easily. And if you look at chlorine, see its electronegativity is 3. This you may remember that electronegativity is the attraction for electrons. So I need to write that down. Maybe that would be smart. So electronegativity. It means attraction for shared electrons. That's about as simple as I can make the definition. So if you're looking at chlorine versus hydrogen, which one attracts electrons more? Chlorine's electronegativity, its attraction for shared electrons is 3. Hydrogen's 2.1. So which end of this bond, which atom will attract electrons more? It'll be the chlorine side. So that means if you have a bond like this, H and Cl, that the Cl is going to be not completely but partially negative, and this is going to be partially positive. Now this little symbol is kind of like an 8th note, is a Greek letter delta. So it shows a partial negative and a partial positive charge. So we would say this molecule has poles. It has a positive pole and a negative pole. It's a polar molecule. It's kind of like a little magnet that it has a north pole to south pole. Right? So polar, the negative end is the chlorine, negative end Cl, positive end H. All right, now what if I have HF? Okay, well look at F. F is 4, H is 1, or 2.1, so 4 and 2.1. So that means the electrons are going to move toward the fluorine again, so that's going to be partially negative, and that's going to be partially positive. So once again, you got a negative end and a positive end. Which one is a stronger magnet? Well, you would know that by looking at the differences between the electronegativity. So let's write those in. In this bond, the chlorine was 3, see it right there. The hydrogen is 2.1. So the difference is 0.9. Down here, the fluorine was 4. See it up here. Hydrogen is still 2.1. And so the difference is 1.9. Now in difference, you know difference means subtraction. All right, so which one has the bigger difference in electronegativities? So this one does. So this one is also polar, but which one is more polar? More polar. And that's the HF, it's more polar. So which one's going to make a stronger magnet? If they were magnets, they're not really magnets, but they kind of act like magnets. Which one would be stronger? Would it be the one that has a bigger difference in electronegativity, or the one with the smaller difference in electronegativity? Well, the one with the bigger difference is more polar, and that would be stronger magnet. It'd be like a stronger magnet. Which means that molecules of HF will attract each other more than molecules of HCl. All right, so that means that affects their properties. It gives them a bigger boiling point, a bigger melting point. If they were drops, remember the drops on a penny? The one that's more polar will be able to pile on more drops. Okay, so that's the background. I'm going to put a little quiz on about electronegativity differences and valence electrons, and it shouldn't be too hard, but it'll make sure that you understand what I'm trying to get across in this video. All right, so I'm going to do one more example, or two more. We'll see which one of these two molecules I'll make up, or two bonds here. If I had C to O, and let's do H to N. Okay, so if you look at the electronegativity of carbon, it's right here, it's 2.5. If you look at the electronegativity of oxygen, it's 3.5. So the difference is 1. I'll write the word difference there to tell us that we're talking about the difference being 1. Look at hydrogen. Remember, hydrogen was 2.1 over here. Nitrogen is 3.0. 3.0. Okay, so the difference is 0.9. So which one is a more polar bond? So the more polar one is the one with the bigger difference. Which end would be more negative? Would it be the O end or the C end? Well, since O is more electronegative, that end becomes negative and that end becomes positive, relatively speaking. I'm going to put the partial sign in there just to remind you that we're not really transferring electrons, we're just sharing them unevenly. All right, so a quick review of what we've said. This is a pair of shared electrons. So when we see bonds like this in this unit, that shows a shared pair of electrons. A shared pair of electrons. A shared pair, a shared pair. They're not sharing them evenly, so just like you often don't share evenly with people. So if the one that gets the bigger possession is the one that's more electronegative, the one that wants it more, which might be somewhat true in life. The people that want it more get more. So the bigger the difference in electronegativity, the more polar they are. So one more quick example of that. Let's suppose I have P bonded to H, and let's suppose I had C bonded to H. Okay, so you look at the electronegativity. H is going to be 2.1 again, 2.1. P was 2.2. If you look right up here, 2.2. C is 2.5. Okay, the difference here, 0.1, difference here, 0.4, which is the more polar bond, the one with a bigger difference. So that one is more polar. Which end is negative in this bond? Would it be the carbon end that's negative or the hydrogen end that's negative? Well, the negative end will be the one that attracts electrons more. So that'd be the carbon end. So that's partially negative, and this is partially positive. If I had another carbon to hydrogen, if that could exist as a molecule by itself, then they would line up like this. So that if this is partially negative, and that's partially positive, partially negative and partially positive, see the negative would attract the positive, and so there'd be an attraction right here. Now, it wouldn't be a physical connection, but it would be in the same way that if you lay two magnets down, they're going to attract each other. Then you could also lay these two molecules down, they would attract each other just like magnets. They wouldn't be physically attached, but they would be attracted. All right, so that's the end of this little introductory video, and I'll post a little quiz about it, and that'll be your next assignment.